Hi Ravi, today we're going to talk a little bit about how to differentiate a function that we haven't really seen before. It's going to look slightly different from what we're used to. And what we've been given is this relationship between these two variables x and y such that the square of x and square of y has to be equal to 4, this constant number 4. Before we even get to the nitty-gritty of math, as you see this relationship between two variables that can be visualized in the xy plane, would you be able to plot this graph? Would you be able to draw it? What does this relationship mean to you?
Okay, so this is making me think a little bit about the Pythagorean theorem, when I see x squared plus y squared must be equal to 4, and I can think of that 4 as 2 squared. And that reminds me of the equation of a circle. And that reminds me of a circle that it's centered around 0, if I remember my lessons from high school well.
Yes, absolutely. Spot on. And even if you don't really remember geometry or trigonometry that well, since that's not really the type of math that we're used to doing in undergraduate or graduate economics, you could do the usual trick of trying to assign different values to x and y and make those values equal to 4, plot that, and you'll see after a few tries that it will resemble a circle. So if I were to plot that circle, it might look something like this. Now, can you tell me a bit, given this specific relationship here, could you tell me a little bit more about information as to, you've already mentioned that this has a center at the origin. Now, what about its radius?
Well, so the radius should be equal to 2.
Absolutely. And as you mentioned from Pythagoras' theorem, we can see here that this c squared can be thought of as the square root of 4. And since radius has to be a positive number, we only think of the positive root of that. Now, going on to what we're actually interested in this question, it's asking us to find dy dx. What do you understand by this expression dy dx?
Well, when I think about derivatives dy dx, I think about how is the variable y changing for a 1 unit change in x.
Yes, absolutely. That's how we're used to talking about derivatives a lot, especially in an economic environment. It's a good thing to keep in mind that ultimately, at the end of the day, what derivatives are doing are that we're taking a tangent line to this original function at a spot that it only touches this function in one point or one set of coordinates, and it's the slope of this line that tells us the rate of change. It's the slope of this tangent that tells us as x changes along the x-axis, what happens to y. And the particular one that I drew here, it's in the quadrant such that values of y are going down as x increases, so it's got a negative slope. And we could have drawn tangential lines to this circle at any point in the circle, really. This is just an example to remind ourselves that what the derivative is doing is looking at this tangent line to this function.
So am I right in saying, so when I think about that derivative, so x changing by 1 unit, that would be approximately right if this change in 1 unit was relatively small?
Exactly, and we have to keep in mind that it's an approximation. It only holds close to the point where the line is tangent to the circle. And as we move further and further away from that point, that's no longer going to hold true. So we need to, quote unquote, zoom in on the point where we're interested in seeing this rate of change. So visually, it might, we've now related this concept of the derivative to a tangential. If we switch back to math, what part A is asking us to do is to find and differentiate the explicit formula of y, which is not really given. How can we get to that formula of y in explicit terms, meaning that we've isolated y on the left-hand side?
I guess rightfully, as you said, we would isolate y, so I would send x on the other side with a negative. And since I want to drop the power of y from 2 to 1, I would just simply take the square root of it.
Absolutely. So what we have come up with now is a function that we're much more used to. We're used to thinking about y on the left-hand side, and then it depends on, in this case, the variable x and the constant 4, and we see that expression on the right-hand side. Thinking back to derivative rules, what would dy dx be in this particular case?
Yeah, so, and before I get to that, is there a particular reason? So I remember that normally when I take a square root of something, I plug in a plus minus in front of it. Is there a particular reason why I didn't plug in a plus minus to the square root?
It's because the question has told us that we should only worry ourselves with the upper semicircle of the set of points in this xy plane satisfying. And that's a really good point. What we're going to be looking at is only the set of points that fall in this part of the circle. And what does it mean about the types of y values that we're not really paying a lot of attention to?
So it seems like if we're just focusing on that upper perimeter of that circle, it looks like y will always be positive.
Absolutely. So I don't have to worry so much here about the negative values that y could take that satisfy this equation, because what I'm ultimately interested in is considering this function in this upper semicircle. But that's a very good question.
Shall we go to the derivative?
Let's do it.
Okay, so what I think of that, I think of square root, which is a function, and I see 4 minus x squared, which is an inside function. So I'm thinking about the chain rule. So I'm going to take the derivative of the outer part, and then I'm going to take the derivative of the inner part. And I quite like to think of the square roots as powers to the 1/2. So thinking of that as power of 1/2. And now I have a little bit of an easier time differentiating the outer function as a power rule. So I would take down the power, 1/2, times the inside, which is 4 minus x squared, and then I would lower the power by -1. And then finally, I would multiply this with the differential of the inside, which is just -2x.
Yes, and what we have here at play is the chain rule, where we have to take the derivative of a function, just like we said, if it helps to rephrase this relationship in terms of a power, that might be more helpful when taking this derivative. What I could do here is that I could simplify things a little bit, and what will happen is that these 2's will cancel out, and what I'll be left with is minus x over the square root of 4 minus x squared. And for all intents and purposes of this part A, we're done. We found the derivative with respect to x of this explicit function y, when y is the square root of 4 minus x squared.
And how did you go from the 4 minus x squared being in the numerator to getting that into the denominator with the square root?
That's a very good question. That's coming from the fact that now this power, 1/2 minus 1, is going to give me a -1/2. And what I'm applying here is the fact that if I have a to the power of -1/2, I can think of this as 1 over the square root of a.
Great, thank you.
Perfect. Now what part B is asking us for is very much the same thing. It's just that what we want to get there through a slightly different way this time around. We have to use implicit differentiation. Do you by any chance remember the formula for implicit differentiation?
Yeah, it's one of those things that I just have to memorize. So I then do dy dx, because that's the thing that I'm looking for, will be a minus in front. And then in the numerator, I will do the partial derivative of my implicit function with respect to y or x. That's something I always forget.
Yeah, it's just a matter of being a bit careful and remembering what this formula looks like. If it helps you to use a bit of a trick when you remember, is that if you're looking at dy dx, we're going to start with partially differentiating the variable that falls in the denominator first.
And what do we mean by f in this particular situation?
So that's exactly what I was going to get to now, because what the question starts with is this relationship, which is specifically telling us that the sum of these two components, this x squared and y squared, has to be equal to 4. But if I want to think about this relationship right here, not as an explicit relationship of y in terms of x, but just as a general function with two arguments, x and y, I could rewrite this such that this function is equal to x squared plus y squared, where this part of the question where they're equal to 4 is just one of the many values that function can take. So that's exactly where this capital F is coming from, is that I think about these two variables as being part of a function that depends on both of them as opposed to only one of them. And that's precisely also where this difference into dows or d's is coming from. dy dx is the total derivative when we have x as an explicit function, as we saw in part A. Whereas now that this function depends on both variables, what I'm going to do is find the partial derivatives with respect to each of them. So what does the numerator look like in this case?
Partial derivative of that expression with respect to x, we're going to treat y as constant, so it's simply going to be 2x.
Absolutely. And similarly, when we get to y, now we think of x as being just a constant because we're ultimately only interested in how changes in y affect this function f. And I'm only going to take the derivative with respect to y, which is going to give me 2y. And simplifying this a little bit gives you minus x over y. And it's here that I have a question for you, because this entire exercise told us to do the same thing, find dy dx, just slightly through two different ways, but ultimately we have to find the same expression. So why is it that I end up with two different expressions?
Well, I think we know that there, in this semicircle, there is an exact relationship between x and y, so I could always rewrite my y as a function of x, and it seems like if I do that, I will get something looking exactly the same like the first one.
Absolutely. So what we have to utilize at this point is that we have to keep in mind that here we're not really done, because we have the derivative of y with respect to x has given us still an answer that's still dependent on the variable y. And I want to have my derivative only in terms of x. So the last step for me to do is to plug in for what y is in this case, which, like we solved in part A, is just the square root of 4 minus x squared. And the moment that I do that, that I isolate the y and then plug it into this derivative that I calculated with the implicit formula, I will retrieve exactly what we ended up having in part A. And now it makes much more sense that we have done the same thing simply in two different ways.
All right. And am I right into saying that up until you got to that minus x over y, you did not use the fact that x squared plus y squared was equal to 4? So
Exactly, and the reason why we didn't use that was because I was so focused on applying the implicit differentiation formula that focuses on this relationship between x and y in the lens of a general function f, this capital F that has these arguments x and y. But the moment that I take a step back and look at the exact relationship between those variables that's given to me by the question, I realize that not only do they have to be related as part of a larger function, but that they have to be exactly equal to 4 in this instance.
Mm-hmm. And can we see some, so as an economist student, can you think of some ways where I'm going to have to apply this particular implicit function?
So the implicit differentiation comes in handy a lot whenever we think about indifference curves and marginal rates of substitution if we are in a setting with only two goods. Mm-hmm. So if you think of this x and y as good 1 and 2, which are the only things that I consume, we can sort of switch the viewpoint a bit here and think of this function that relates both of them as a utility function. Mm. So the moment that I think of this f of x and y as, say, a function u xy, and I know that there could be a lot of different shapes of relationships for these two goods, x and y, that do affect my utility. If we take an example such as this one, I know that I can, for fixed levels of utility, go and draw indifference curves, and then the slope of the tangential to that indifference curve will tell me exactly at what rate am I willing to sacrifice 1 unit of one good to get more units from the other good.
Great.
Yeah.
Yeah.
We'll leave it there.
Okay. Yeah, we'll leave it there. I mean, I could have. Yeah, I'll leave it here and I'll cut that out.
Because I was wondering about time.
Time as well. Yeah.
Which is why I was talking quite fast towards the end.
Yeah. We'll get better at this.
Yeah, but also